Okay, let's talk about probability. So today I'm going to talk about continuous probability, and I'm using the word continuous to draw a distinction between this and discrete probability. Discrete probability is when you have a random, let's say a random number that could only be finitely many things. Like if you're rolling a die, the number is either 1, 2, 3, 4, 5, or 6. It can't be in between those numbers. It can't. There's only 6 possibilities. Continuous probability is when we have a random number that could. One example is that it could be any real number at all. It doesn't have to be allowed to be any real number, but that gives you an idea of what we're talking about there. There's infinitely many possibilities. And the way we talk about the distribution of such a function is we say that it has a probability density function. So there's this function f of x, and the way that I find probabilities here, like if I want to find the probability that my random number x is in between a and b, that's the integral from a to b of this function f of x. That's what we do with the probability density function. And we require that the density function is greater than or equal to 0. Roughly speaking, we're not going to talk about negative probabilities. We're not going to say that the probability that x is between two numbers is ever negative. So this function is never going to be negative. And also, this is referred to as the law of total probability sometimes. This is basically the fact that if I take all of the possibilities for my random number x, and so all of the possibilities are from negative infinity to infinity, and I ask what's the probability of like putting that all together, like what's the probability that x is anything, that should be 1. So in probability, so sometimes people talk about probability in terms of percents. So they would say probability of 100% is the whole thing. That's like what I'm saying. We're just not using percents. So we say the probability of the whole world adds up to 1. One more thing before I get into an example. We say that a random variable has an average value, or sometimes expected value, or also sometimes just the word mean. So it's given by this formula. So it's the integral of from negative infinity to infinity of x times f of x. This is like taking the number x times the probability of getting x and adding that all up for all possible values of x. This is basically, well, it's what it sounds like. We have a random number, but it has an average. Like if I were to just generate this random number again and again and again, I would get all these different values. But if I average them together, it would be very likely close to this. That's what we're talking about here. All right, so let's do a concrete example. And this is going to be kind of a baby example, but that's maybe good for our first one. I'm giving a function f of x, and this is a pretty simple function. It's just 1 if x is between 0 and 1, and then it's 0 otherwise. This is what we call a uniform distribution because it's constant. Well, it's 0 almost everywhere, and then the spots where it isn't 0, it's just a constant. So this is what we call a uniform distribution because roughly speaking, it's out of the numbers that it could possibly take, which are the numbers between 0 and 1. Well, because I'm just saying that it's probability 0 outside of that interval. But between 0 and 1, it's sort of, roughly speaking, equally likely to be anything between 0 and 1. That's why we call it the uniform distribution, the fact that it's sort of equally likely to be anything. So let's verify that this is a probability density function, and let's find the mean. So We have our requirements to be a probability distribution function, so that's this and this. So f of x is supposed to be greater than or equal to 0. Well, let's just look. I mean, f of x only takes two values. There's 1, which is greater than or equal to 0, and then there's 0, which is also greater than or equal to 0. So I can check this just by looking. There's kind of nothing really to do there, so I'll just put a check mark. Let's check the other one. Integral negative infinity to infinity f of x dx. So in general, this can be, I mean, the way it's written, it's like an improper integral because you always have negative infinity, infinity, and the limits of integration. However, this function, and this is fairly common with probability, our function is 0 almost everywhere. Like if x is less than 0 or greater than 1, this function is just 0. So I might as well just integrate over the interval where f is not 0. That's going to give me the same answer. I can drop off all of the values of x where f of x is 0. So I can just integrate here. And between 0 and 1, I'm just going to use this value. So this just turned into the easiest integral ever. Antiderivative is x. Plug in 1, plug in 0. We get 1. Of course, we should know that we're supposed to get 1 because we're checking that this is a probability distribution function, and so we're checking that this integral is supposed to be 1. Indeed it is. All right. So it's a probability density function, so let's find the mean. And by the way, before we go in and find the mean, I'm going to use the formula to find the mean, but we should basically know intuitively what the mean is based on the fact that, so how did I describe the mean? It's like if I generate this random number again and again and again, and I'll get a bunch of different values, but I average them together, the answer should be close to this number that we call the mean. So let's imagine, because this is describing a random number between 0 and 1, and it's uniformly distributed. It's equally likely to be in any part, like it's equally likely to be farther to the left, it's equally likely to be farther to the right. So it's the uniform distribution. So I generate that again and again. I get all these numbers between 0 and 1, and then I average them together. Intuitively, we would expect the average to be a half, just because it's right in the middle between 0 and 1. So we should expect this mean to be a half. But let's use the formula and see what we get. Oops. First of all, I get to do the same thing. Because f of x is 0 almost everywhere, I can just integrate over the interval where it's non-zero. So for those values of x, f is just 1. So I'm just doing x times 1. So this just turned into another really easy integral. Antiderivative of x is 1/2 x squared. Plug in these guys. I get a half minus 0, which is the answer we expected. All right. So like I said, the one we just did was kind of like that was a probability distribution function for babies, or that's a good first example to do. And uniform distributions are important, but they're pretty easy to deal with. So let's talk at least briefly about more complicated and maybe you could say more like having to do with the real world or interesting situations from the real world. So this is the bell curve. You've probably all seen a graph of the bell curve. A random variable whose distribution function is given by this function is said to be normally distributed. It's this distribution function. It's a bit weird looking. It involves the square root of 2 pi. And by the way, for people who have really seen this before, which I don't assume is everybody, but for people who have really seen this before, this is a normal distribution, assuming that it has a mean of 0 and a standard deviation of 1. You can have a normal distribution with any mean and any standard deviation, but in this case I chose 0 and 1. So what do I want to say about this? So here's a fun fact. In order to be the distribution function, I'm supposed to be able to integrate from negative infinity to infinity, and I'm supposed to get 1. This is true. It is not obvious at all. At least for us in Calc 2, we wouldn't have any way of really evaluating this. This is a fact that if it can be covered in Calc 3, or at least once you're through with Calc 3, you'll have the tools to deal with this fact. But for right now, I'm just going to tell you that it's true. So what do we want to do here? Let's, just for an exercise, let's estimate the probability that our random variable is between -1 and 1, if x has this distribution function. And this is a little bit of a vague question on purpose. We're not told to use any particular method to estimate this. I have one in mind, so you'll see what I do when I do it. Well, first of all, how do I find the probability that x is between two numbers? Well, that's what my distribution function is for. I integrate from here to here. Of what my function is. Okay. Now, we're in a bit of trouble, and this is why we are using the word estimate. We cannot find this antiderivative. No matter what we try, we will never find this antiderivative, at least in terms of elementary functions. It looks sort of tempting to try a substitution, like maybe w equals -x squared over 2, but you're going to have trouble making that work because there's nothing to be your dw, basically. And it's actually known, and this is kind of beyond the scope of Calc 2, but it's known that this is not an elementary function, that the antiderivative of this is not an elementary function. So we're never going to be able to evaluate this the normal way. But we recently learned some facts about Taylor series, and that's the approach I'm going to take. So before I do, let me just mention, of course, this is also something that maybe we could do with like the trapezoid rule or with Simpson's rule, which are other things that we learned for estimating integrals when you can't find the antiderivative. So I just want to throw those ideas out there. That's not the direction I'm going to take, but those are ideas. You could use trapezoid rule or really any of the rules that we use for numerical integration, like Simpson's rule, to approximate this. I'm going to use Taylor series, though. Recall e to the x equals... We've seen this before. I'm just reminding you. So, let's see here. Maybe I'll pull out 1 over square root of 2 pi. And then I've got e to this. So that's a series. It's like this, except I'm replacing all the x's with -x squared over 2. like that. Okay. Let's simplify this just a little bit. I'd like to separate off my power of x. So maybe I'll leave myself some space and write x to the 2n up there because I see an x squared raised to the n. And then let me figure out what to write in front. Probably a fraction with an n factorial on the bottom to take care of that. And what am I missing? So I took the x squared out. Basically, I'm missing negative 1/2 to the n. Actually, I'm lazy. I'm just going to write negative 1/2 to the n like that. One alternative idea is like I could write negative 1 to the n on the top and then a 2 to the n on the bottom. I think I'm just going to leave it like this. I don't feel the need to do anything else. Now that I have my power of x separated, let's find the antiderivative. So this is... So I'm doing the antiderivative. I have limits of integration, so there's not going to be a plus c when I find this antiderivative. I'm just going to do what I normally do. So I've got my stuff that only depends on n, and that carries right through. And then I've got my power of x, and I do that the way we do powers of x. I increase the power by 1, and then I divide by that same number. And this was a definite integral, so I would plug in negative 1 and 1. So let me plug these in. Okay, when I put in 1 for x, of course 1 to any power is just 1, so I'm going to get this, and this is just a 1 over 2n plus 1, so we'll put the 2n plus 1 down here and call that good. And I plug in negative 1 for x, and actually, yeah, I'm just noticing something funny here. When I put in negative 1 for x, I have negative 1 raised to an odd power, which is just negative 1. Right, negative 1 to the 2n plus 1 is always just going to be negative 1. In fact, yeah, I'm not really crazy about, I'm not really going to try very hard to simplify this series because I just want to be done with this problem, but I could make this a plus and make this a plus. And then basically I'm looking at 2 copies of the same exact series. So I could just like find this one and double it. But anyway, let me wrap this up. Our instructions were to estimate it. What we did was we found this as a series, and in order to estimate it, I'm just going to, I just used a calculator, a computer. But I'll tell you what I did, just so you know. We expressed our answer as infinite series, and of course we can always estimate the sum of an infinite series, assuming it converges, by just adding up enough terms. So I can start with n equals 0 and then add up the term that I get for n equals 1, 2, 3. And if I go far enough, and we have theorems about how far you need to go in order to make sure that you've gotten close to the answer. But let me just tell you that if you add up a lot of terms, you will get that this is approximately, let's see, I wrote this down somewhere. 0.68. And the reason why I did this example is because, again, I know not everybody is a statistics major or has really taken a statistics class, but for people who are familiar with the normal distribution, this is actually a familiar fact that we just went over. This is a normal distribution with a mean of 0 and a standard deviation of 1. So what we just found was the probability that our random variable was between -1 and 1. In other words, this is the range that's within one standard deviation of the mean, because the standard deviation is 1 and the mean is 0. So this is the range that's within one. It's within a distance of 1 from 0. And this is a familiar fact to people who know that the normal distribution, the probability of being within one standard deviation of the mean, oops, struggling here, is about 68%. People memorize these numbers. There's also, like, I think the probability of being within 2 standard deviations from the mean is, I think, 95%. So people remember that one, assuming that I have it right. But anyway, so that's the fact that we just went over, and we did it using Taylor series.